In this video, I'm going to be showing off a Nintendo emulator that I wrote in Rust, and alongside it, I'm going to be showing off the graphical debugger that I wrote, written in Elm, which runs in the browser. So right here, this is how I will invoke the emulator, which is really just telling it to compile and run it with the debugger feature enabled. If I were to omit this debugger feature, it would compile it without the debugger, which is cool because if you don't want the overhead introduced by the debugger, you can compile it without, and then you can get the increased performance and reduced binary size. So we'll run that, and we get some debug output. Basically, it's starting an HTTP server and a WebSocket server, which it uses to communicate with the remote debugger, and then it's we're just kind of waiting now for the debugger to attach. So it just kind of pauses execution until the debugger attaches. So over here on the Elm side, I'm using Webpack to kind of compile everything and run it on a dev server. So just run this command. Elm does its thing, npm does its thing, Webpack does its thing, and now you should be able to access it in the browser. So this is basically what we get once the debugger attaches, and I'll kind of go through everything here and explain what it is. Up here we have the status of the CPU. So what we see here are the various registers. We have the program counter, which points to the next instruction to be executed, the memory location where it resides. In this case, you see we're paused where the program counter says we should be, which is hex 8000. And the first instruction that we will execute is the SEI instruction. Stack pointer register indicates the next available spot on the stack, and it grows downward. So as you push things onto the stack, it decrements, and as you pop things from the stack, it increments. The accumulator is typically used to store values temporarily or store the result of some instruction. The X and Y registers are typically used for memory indexing. So like if you wanted to read over a bunch of bytes contiguously, you would increment the X register or Y register and then execute the necessary instruction. This register here is called the status register. It is a bunch of bit flags that indicate the status of various parts of the CPU. And then here we have a cycle counter, which is not part of the CPU. It's just generally useful for various things. Down here we have the compiled disassembly. We have a gutter where we can set breakpoints. And we have the memory offset where the instruction lives in the address space. Over here we kind of have a preview. It's like a memory preview. Any instructions that reference a memory location will display what I call the resolved memory location, and then the value in memory there. When I say the resolved memory location, some instructions might specify a fixed memory location. Some might use the memory indexing that I alluded to earlier, which is to say it specifies a memory location, and then that is offset by, in this case, this instruction here, the X register. And so it'd be hard to kind of, figure out that memory location in your head and then kind of pick it out of this mess of bytes. So for convenience sake, over here, this is the resolved address when taking the X register into account, and then the memory address at that location. These will also change as instructions are executed and these registers are updated, but they're all 0 right now. So over here, we have basically a dump of all the addressable memory, the memory basically that the CPU has access to. There's 16 kilobytes of it, kind of broken up into discrete parts, not just like a big chunk of memory that the CPU can do whatever it wants with. But this first big chunk of memory, which actually extends beyond the area I'm scrolling in, is all RAM. And within here, you have the stack space. So starting here, which is where the stack starts and grows down to here, is 256 bytes of stack space. If you ever wondered why developers back in the 80s writing Nintendo games weren't using things like C or C++, well, this was one reason. With 256 bytes of stack space, having like a function call ABI that when itself just exhaust all your stack space would be really difficult. And at that point, you'd be writing such constrained C or whatever that like it wouldn't even be worth it. So the other thing too is 6502 assembly was designed to be written by humans. It's not, there's not like hundreds and hundreds of instructions. It's not like x86 assembly where you would have to be a superhuman to be able to write it, efficiently and know all the various instructions, because there's so many and there's so many specialized instructions. It's really, modern assembly is meant to be omitted by compilers, not written by hand. But it was a different time back then. And in large part because we were working on such constrained hardware. Other parts of this, the memory space, are, well, a lot of it's mirrored. So for example, this RAM is mirrored, I believe, 4 times in subsequent chunks of like 8 kilobytes or something. Some of it's mapped to various registers on other hardware within the Nintendo. For example, the PPU, which is a picture processing unit, the APU, which is audio processing unit, the controller inputs. So if you wanted to read the state of a controller at any given time, you would just read a specific memory address, and that would give you the state of the controller. Then another part of this memory space is mapped directly to the cartridge itself. So the cartridge contains like the program data, which is the machine code that we've disassembled here. It contains what is called character data, which is really just like tile information. So the tiles that make up the graphics on the screen. And then it could also be mapped to RAM on the card itself. So if you wanted to save your game, some games allowed you to save the game, there's a specific address range where you would write to write the save state. Over here we have a screen buffer. This basically represents what the PPU is outputted. So in the original NES, it was writing out to, or basically drawing onto a CRT monitor. Since this is an emulator, it's writing to a frame buffer, and we display that here so you can kind of see what is being output by the PPU. We can start stepping through this and actually seeing stuff happen. So as we do that, see the program counter incrementing, you see some of the registers changing. So this X register is now got a value of 256 and or 255, and any instructions that use that use X indexing will be reflected. So for example, this instruction here uses a base address of hex 77 offset by X, which resolves to this memory address, which currently has a value of 0. So we keep stepping through that. And you see we're kind of stuck in this loop here, going between these 2 instructions. This was load into the accumulator, the value and memory address, hex 2002. Over here we see that's 0. So it's loading 0 into the accumulator, and then this instruction is basically branch on non-zero value in the accumulator. So what this will do is, if it is 0, it takes this branch, and this is a relative offset, and so this is basically telling it to branch back to the previous instruction if the accumulator is 0. So this is effectively an endless loop, right? Because there's nothing in the program code, at least, that's updating this value in memory, and we just keep them between the 2. But what's actually happening here is this is one of those special addresses, this map to the PPU. the picture processing unit, and it's the status register. So eventually this will be non-zero once the PPU has initialized. So we could do this long enough and we'll eventually get through it, but that would take forever. It actually takes a couple thousand cycles for the PPU to initialize. So what we can do instead is set a breakpoint somewhere. Then we can just continue. Then we hit the breakpoint. We jumped, like 100,000 cycles have elapsed. We got a bunch of stuff written into memory now. You can see some values pushed onto the stack. Yeah, so this is still a lot of initialization logic though. Nothing super interesting is happening at this point. So what we're going to do is set a different type of breakpoint. And we do that by bringing up this little console here. So when I want to enter in a command, I just hit the / and this little command box pops up, and then I can enter a command. In this case, BP for breakpoint and NMI for non-maskable interrupt. A non-maskable interrupt is the type of interrupt that the PPU generates when it's finished rendering a frame. And it's an indication to the CPU that it needs to stop what it's doing since the frame is done rendering and it has some number of cycles before it's going to start rendering the next frame. In those number of cycles, it's got to go and load any of the tile information into RAM so it's available to the PPU to render the next frame. So you have some kind of fixed allotted amount of time to do that in the non-maskable interrupt handler. And so what this does, the NMI too is it's also kind of like a dynamic breakpoint. The interrupt handler is at a memory location specified by the cartridge itself. It stores a memory location at a specific memory address, and that memory location is what we're actually jumping to. And so that's basically the handler for when we're done rendering a frame and we need to load graphical data for the next frame. So we're going to set that, and now we'll break on the interrupt handler for when the PPU is done rendering a frame. I just want to show one more thing too with breakpoints. We can also specify just a memory offset to set a breakpoint in here as well. So we can set something that's going to show up. So I just set a breakpoint here and just saw it pop up. So that's pretty cool. So we're going to continue now and wait till we hit the interrupt handler, and you can see down here in status, we are breaking on the non-maskable interrupt. So this is the location of the interrupt handler. You can essentially think of this as a subroutine that again handles loading the tile information for the next frame into memory so that the PPU can start rendering it. So we're actually going to go through a few cycles here. So you see we're breaking on the interrupt handler a number of times. The frame buffer isn't updating, and that's because we're still pretty much initializing the Nintendo at this point. It's reading all the graphical data, a bunch of data, putting in the correct locations so that it can be rendered. So the PPU is doing its thing, but there's a setting on the PPU that says basically don't actually put anything onto the screen because it would be garbage at this point. So eventually, once everything's kind of initialized, that's when you get the first actual frame being output. And as you can see now, we have the first frame rendered of the title screen. It would be really cumbersome to keep doing this until things actually start animating, because we're doing one frame at a time very slowly. So we're not going to do that. So instead, I'm just going to kind of show this thing really briefly, running it real time. So we're going to stop this. And you might notice here that I'm compiling it without the debugger. So when I run it in real time, we're not paying any of the price of having the debugger in there. It would be possible to compile it with the debugger as well, but we're not doing that here. So here it is. Something with OBS, the software I'm using to record this, interferes with me being able to actually use the inputs for some reason. So I'm not actually able to play it myself, but you can watch the demo run. As you see, it's running at full speed, and pretty accurate. There's some graphical glitches. There's a particular PPU bug that I was never able to squash. So that's why some of the tiles are a little off-colored, see here. But otherwise, it works great. It only works with earlier NES games. It's part of emulating a Nintendo. One of the other things you had to emulate was the various chips that were on the carts. So they were called mappers, and they kind of dictate how the memory addressable to the CPU is mapped to the various parts of the cart, along with other things. And that's how a lot of how Nintendo games evolved, was through these various mappers that did more and more complex things and kind of helped overcome some of the limitations of the Nintendo. And so I'm only emulating the it's called NROM, which is the most basic mapper. So it only plays a handful of games. But the games it does play, it plays pretty well. Okay. I do want to talk about one more thing here, and that is Elm specifically. Both languages I use to write this I like a lot, Rust and Elm. But Elm is a bit special because it was the first time I felt like I could leverage the browser the way it was really meant to be leveraged. When you think about it, web browsers are really amazing runtime that we just have really terrible means of controlling it. And those means are JavaScript, HTML markup, and CSS. And in fact, oftentimes when we're writing a web application, we don't actually use any of those technologies in a vanilla fashion. We're at least transforming the JS using a newer version of JavaScript, or transpiling it from TypeScript or Flow or whatever your choice, your preference is. And we talk about CSS. How often do we write CSS by hand? We're writing Sass typically because it makes our lives easier. So I guess the point I'm getting at is a lot of these technologies in the browser, nobody actually wants to use them as is. And that's the really cool thing about Elm, is that all these kind of separate technologies can kind of be used holistically in Elm. And I'm going to give a small example of that. So this is the code for the debugger front end. And I'm going to show you the view function. And so this is kind of like the top level view function, which basically determines all the HTML to be rendered to the page. One thing I want to mention real quick is that Elm uses a similar virtual DOM concept that React uses, so it is really efficient with its updates, and so that's nice. Like it's actually really performant too. Anyway, this here, if you look at it, you can see that it's actually structured almost identically to normal HTML. It's just structured using Elm. And what we have is, like, for example, here, a div function. The div function takes a list of attributes, and then it also takes a list of child elements. So in that regard, we're essentially writing HTML. We're just writing it in Elm. The benefit of that being, Elm is a statically typed language, and we have a compiler kind of going over this and making sure that all the syntax is correct before we actually run the application. So kind of have an extra set of eyes on this, making sure that it's all well formed. Something you don't really get with HTML. But there's more. So see, we're specifying an ID here on this div, and we're not specifying a string literal, we're actually specifying an Elm value. And so this container is defined as part of a bunch of styles that are part of this ID type. So these are all the different IDs used throughout the application. And these are all the different classes used throughout the application. Now think about a web application that you may have written, and how hard would it be to identify all the different classes and IDs used throughout it? It'd probably be pretty difficult. They're probably scattered everywhere. They're probably pretty inconsistent after a while, over a number of years with enough people hacking on it. And here we see everything, and we can find all the references to them too. We can find where all these things are used using standard IDE functionality, or not. One of these will probably work. Okay. Anyway, this should work. Usually does work, but it might be a bug. Anyway, so we covered the markup, right? We're defining our markup in Elm. As you can also see, our program logic is written in Elm. So we've already covered like two parts of what makes up the browser runtime: the markup, HTML, and the logic, which would typically be written in JavaScript. We're doing that all in Elm here. So what's the other thing? Styling, CSS. So we're actually doing that in Elm too. So this is this is where we declare all the styles for the application. Again, you see we're using the same styles that we defined over here. So we're using the same values to declare the styles as we are to declare IDs on elements. And that means that, for example, we can refactor them and make sure they're updated everywhere they're referenced. If you happen to type in, a style or an ID that doesn't exist, you get a warning in the IDE before you even run the thing. So that's insanely useful. Those are the type of things that, especially in a personal project, that just kind of wear down your resolve to keep hacking away at something. All the small little time wasters that build up, all the little context switches switching between, Sass or CSS and HTML and, JavaScript. And JavaScript itself has its own set of quirks. And as you can see here, we're defining everything in the same language, and it's all type checked holistically. Everything is kind of cross-referenced as part of the compilation step, and it only compiles if it's all correct. Now you could have logic errors, of course, but that's different. That's, the compiler is really helping us out here and allowing us to do what we do best as programmers. And if we do make a mistake, it's kind of mistake that can't be caught by a tool. So going back to the example of, like, if you had to catalog all the IDs or classes used by an application, or say you wanted to rename an ID or a class, and in a typical web application, that'd be referenced in probably a number of style sheets, be referenced probably in a number of places, potentially in the JavaScript and also in your HTML. You would need to grep your code base for this string and then do essentially find and replace, which is potentially kind of dangerous and error prone. And verifying that every place that got updated would be verifying that it all worked would be very cumbersome. And something like that could potentially take days. So to prove that the IDE typically does work, when I was trying to navigate, it didn't for whatever reason, but we can rename this, for example. We can rename hex editor to whatever we want. We'll just screw up and just throw some random characters in there. And if we look at the version control settings here, you can actually see that everywhere that was referenced, it was updated. And if we go back here, we can recompile the app. Also restart this. And we'll open the browser, and you can see it all compiled successfully. Everything's working fine. Like I said, usually if it compiles in Elm, things are going to work. If they don't work, it's probably a logic error. And so I basically changed an ID that is referenced in CSS, it's referenced in the markup, it's referenced in the program logic, and I was able to do it as fast as a IDE is able to refactor something which is, on the order of milliseconds, and that's pretty amazing. And the other cool thing too is like you're not constantly context switching. I have styles living side by side with my markup and application logic. And while that might be a subjective thing, how it's organized, the fact remains that I'm still just writing Elm for everything. And that's, it's just a less cognitive overhead. And that's really why I was able to make something that it truly felt like an application running in the browser, because, Elm really helps you manage complexity, and you can just continue hacking on it and it still is fun. If I were to do this in JavaScript or even something like TypeScript, as I have done many times in the past, eventually something, especially as complicated as this, will collapse under the weight of its own complexity, and it just doesn't become fun and you stop hacking on it. And I hacked on the debugger front end for the good part of a year, just, whatever my imagination could think of to add to it, I was pretty much able to implement. And that's a really cool feeling, especially when we're operating in the browser, which is typically a really hard thing to leverage, especially for as amazing a piece of technology it really is. So yeah, I highly suggest, if you're doing front-end web development, go check out Elm. And also, if you've been kind of intimidated by functional programming in the past, Elm does make a point of being very approachable and accessible. And you're not going to be inundated with all these really high-level concepts. You're not going to have to try to figure out what the hell a monad is or anything like that. So yeah, go check it out. And thanks for taking a look.